Good afternoon. On behalf of the Lectureship Committee, I would like to welcome you to the 104th in this series of distinguished lectures. Today's BSA Distinguished Lecturer is Dr. Nima Arkani-Hamed. Dr. Arkani-Hamed is a theorist with wide-ranging interest in fundamental physics, from quantum field theory and string theory to cosmology and collider physics. He received his Bachelor of Science in Physics and Mathematics from the University of Toronto in 1993, his PhD in Physics from UC Berkeley in 1997, and did postdoctoral work at Stanford Linear Accelerator Center before joining the Berkeley faculty in 1999. In 2001, he joined the physics department at Harvard as a professor of physics before moving to his current position as professor in the School of Natural Sciences at the Institute for Advanced Study in 2008. A member of the American Academy of Arts and Sciences, he was awarded the Gribov Medal of the European Physical Society in 2003, the Raymond and Beverly Sackler Prize given at Tel Aviv University in 2008, and delivered the Messenger Lectures at Cornell in 2010. And this was the biographical sketch provided to me on behalf of the BSA Lectureship. So I'd just like to take a minute and say something more personal. I first met Professor Arkani-Hamed fresh out of grad school when I went to Stanford Linear Accelerator Center as a research associate, where he was a young postdoc, although that's not the impression you got from him once you started talking to him about physics. From that very early time, he was quite distinguished with his insights and perspectives that he brought to various problems of theoretical physics. Since those days, in the late 90s, he's been the source of a number of very influential ideas in our field of theoretical particle physics. And many of these ideas not only shaped the direction of progress in theoretical physics over the last 12 or so years since those days, they have also had a major impact on the direction of experimental searches that are going on, for example, at Large Hadron Collider in CERN. And of course, his influential ideas are just too many for me to get into today and have even a brief description of. However, I think it's fair to say that whatever problem he's always tackled, a hallmark of his research has been, at least to me, bringing fresh perspectives and insights to problems that have existed for a long time. And I think I have very little doubt that fresh perspective and insight is something that you would take away from his lecture today as well. So without further ado, I cede the podium to our distinguished speaker, ladies and gentlemen, Professor Nima Arkani-Hamed.
Well, it's wonderful to be here at Brookhaven, as always, and especially wonderful in this particular period, as you've heard from Human already. There's an exciting program going on right now. The Brookhaven Forum is devoted to the physics of the Large Hadron Collider. And that's really the really big news in fundamental physics in the past number of years, and likely in this decade, is to come to grips with whatever it is we're going to learn from this spectacular experimental facility. So what I want to do today is tell you about the physics associated with the Large Hadron Collider. I'm going to do it in perhaps a slightly unconventional style, which is to put this physics in a somewhat broader context, to actually step back a little bit and put the physics of the LHC in what I think is its proper historical perspective. Stepping back a bit is going to take us back to the turn of the century and the revolutions that started off 20th century physics, the revolutions of relativity and quantum mechanics, the space-time and quantum mechanics in the title. And we've learned an enormous amount about how these revolutionary ideas play together. We've learned an enormous amount about how to use them to, in a very precise and beautiful way, describe all the known interactions and particles and forces that we see around us in nature. But one of the things I want you to take away from this talk is that some of the bedrock foundations on which these ideas are built lead to rather severe paradoxes, really severe paradoxes in our understanding of nature about incredibly basic questions. And normally when this sort of thing happens in physics, there are incredibly simple basic questions that you have ridiculous answers to. It tells you that you're missing something very big, not likely a detail, but you're missing something very, very big. These questions have been around for a long time. So it's not that they just happen to come up in the last 10, 20 years or so. The basic questions have been around for a long time. And there have been a lot of attempts at reaching some theoretical understanding or finding some resolutions to these paradoxes that I'll tell you about. But what's particularly exciting is that we're in an era now where we're probing the distance scales or the energy scales where we expect answers to at least some of these questions. And that's what we hope the LHC will do for us. So that's really what I want to tell you about. What the sort of very, very big picture issues are that we have to confront and how it is that the LHC will go about addressing them. So let's start. I'm going to try to summarize the last 400 years of physics in a few slides. But just at a very basic level, our picture of the world today is governed by a number of basic forces or interactions. The most familiar ones are like gravity, that keeps the Earth going around the moon, the sun, keeps the moon going around the Earth, keeps our feet to the ground. God knows what it does to my brain. Electromagnetism, that was, again, something that was discovered by the ancients. They knew there was phenomena like thunder and lightning. They knew there were phenomena that some funny stones had strange magnetic properties. They attracted and repelled each other. So these are interactions we've known about for a long time, but we now understand, or we've understood for a long time in a more unified framework of electromagnetism, as well as some less familiar interactions that are still play an important role in even controlling the everyday world around us. There are the so-called weak and strong nuclear forces. The weak nuclear force is associated with the radioactivity. The strong nuclear force, originally, its earliest manifestation was keeping protons and neutrons locked up together inside the nuclei of atoms. So we have these four basic interactions, and they hold sway over an enormous range of distances. So here we have a sort of cartoon of all the distance scales that we know about in the universe, starting at the very, very largest distances, around 10 to the 28 centimeters. It's around 10 billion light years. That's about the size of the observable universe, which is happily expanding there. You will have to forgive the terrible artwork throughout this lecture. So if you're suffering, I'm suffering too. And then basically every decade of distance as we go to a shorter scale, something new and interesting happens. I've only represented some of them. You know, galaxies are around 1 million times smaller than the universe. The Earth is around 10 to the 13 centimeters from the sun. There's people, you and me, DNA, atoms, and protons and neutrons are around 10 to the minus 14 centimeters in size. And going down, so this is obviously an important distance scale, the size of the observable universe. There's another important distance scale many of you haven't heard of, which is around 10 to the minus 17 centimeters. And it has a name. It's had a name for a long time. It's called the weak scale. For a variety of reasons, we think it's associated with with the weak interaction that I told you about a second ago. But for the moment, you just need to know it's a really, really tiny distance scale, around 1,000 times smaller than protons and neutrons. But just like there's something sort of invariantly important about this long-distance scale compared to all the other scales. It's not some random scale. It's the biggest scale. It's the size of the observed universe. There's also something important about this scale. There's some very interesting physics that takes place at this scale that I'll be telling you a little bit more about. But it just so also happens to be that, well, of course, there's a frontier of our experimental understanding of the universe. Out to the very biggest distances, we have various cosmological experiments that I won't have time to tell you about today. But there's a frontier at the very, very shortest distances. We probe these very short distances using very, very high energy particle accelerators, for a reason that we'll get into in a second. And this is where the LHC is about to go. It's about to probe the laws of physics at distances around 1,000 times smaller than the nucleus. The previous highest energy accelerators we had in the world, for example, out at the Fermilab just outside of Chicago, went to a distance around 10 to the minus 16 centimeters, and so we're going roughly another order of magnitude beyond that, to around 10 to the minus 17 centimeters. Just so you have some idea, every order of magnitude in this business, every factor of 10 hurts. Okay? Every factor of 10 comes at significant cost, not monetary cost, intellectual cost, every cost. Just to put in some perspective, in the 1950s, we were probing distances roughly at around 10 to the minus 14 centimeters. And so it's taken us 60 years to go this sort of 3 orders of magnitude, between 10 to the minus 14 centimeters to 10 to the minus 17 centimeters. And this jump from 10 to the minus 16 to 10 to the minus 17 centimeters is really something that many of us in this subject have been waiting for on the order of 2 decades. So this is now a once-in-a-generation kind of thing that happens, that you get to take these factors of 10 steps to a shorter distances. What's particularly exciting is that, as I mentioned already, we happen to be probing territory where, for completely independent reasons, we suspect something should be going on there, and so we're going to be learning what that something is. All right. Now, let me clean up this picture a little bit. So in the sort of fundamental physics that we think about, there's all sorts of other wonderful phenomena in physics happening at other distance scales, but we tend to concentrate on a few that we suspect are closely tied to the deeper conceptual issues of what the underlying laws of nature actually are. So the entire previous slide is collapsed to be between these two lines. There's the 10 to the 28 centimeters, the 10 to the minus 17 centimeters, and I've added one more really, really tiny distance scale. It also has a name. It's the Planck length. It's around 10 to the minus 33 centimeters. As I'll explain in a second, this scale is actually is associated with gravity in a way that I'll explain in a second. So these are really the distance scales that we tend to think a lot about in our business. The experimental frontier is here and there, I remind you. This is something that's a pure theoretical extrapolation, but we think there's something important happening there as well. And all of this picture of the scales that we think about, every single line in this picture is associated with some essential crisis in our understanding of physics. So, as I'll review in a second, when we talk about crises, we sort of have high standards for crises, because appreciating these crises is only possible built on a foundation of a theory that works spectacularly well at describing almost everything that we see. It's only because we're able to sort of sit on this mountaintop and look out that we can actually appreciate what some even deeper and more pressing problems are. But we are at that mountaintop. We can look out and see what else there is out there. And what we see out there are some really enormous, looming conceptual challenges that will likely be involved with the conceptual revolutions of the 21st century, just as relativity and quantum mechanics were the revolutions of the 20th century. For instance, the physics-associated, a number of thought experiments suggest that down here at around 10 to the minus 33 centimeters, the effects of quantum mechanics and gravity have got to be taken into account simultaneously. So this is a subject of quantum gravity. But the shock here isn't that we don't know how to put these words, quantum mechanics and gravity, together, but that these thought experiments lead to a really startling conclusion, that the very notion of space-time itself has got to disappear and be replaced with something deeper and more primitive. That's a very startling conclusion, because physics, if nothing else, has been for 2,000 years, or for 400 years, a story of understanding how things take place in space and time, and yet we suspect that we have to lose this notion of space-time at a fundamental level. That's one crisis. The other crisis turns out to have a very, very different character. A really salient feature of this picture of all these different scales that we have is that there are really enormous separations between them. We have a really gigantic universe. It's a nice, big, comfortable place. We live in it. We walk around. It's a nice, big place. And yet, the fundamental laws operate on microscopic scales, involving really tiny things like atoms, nuclei, and physics at even shorter and shorter distances. This may not at first seem like such a terrible paradox, but as we'll see in a second, it's a really massive paradox. In our best current understanding of physics, it seems wildly implausible that there would be any sort of macroscopic universe at all. And yet, here we are living in a nice, big, gigantic, macroscopic, huge universe. So there are sort of two questions here. There's three scales, so there's two gigantic separations, and each one of them is associated with an essential paradox in our understanding of nature. Okay? But the basic question is to try to understand why there's a big universe at all. I'll try to explain why that's actually a paradox. All right, so those are the problems. But now let me spend a few minutes telling you what all the successes have been for the last 400 years so that we can get to the point where we can appreciate what the problems are and then ultimately what we hope to learn about these problems, at least some of these problems, from the LHC. So this is the story of the last 400 years condensed to a few slides. And the one slogan, really since Newton, who kicked off this particular approach to doing science that we continue today in theoretical physics, the slogan is that of unification. It's to understand that seemingly widely divergent phenomena are actually different aspects of the same thing when more deeply understood. So this started with Newton's famous leap that the same force of gravity tugging the apple to the Earth actually kept the moon going around the Earth. I did it right that time, okay? And now, that's not at all obvious. It's totally unobvious, and it took Newton's staggering genius to realize that these two things are actually the same thing. Of course, today we're so used to it, we teach it in, well, whenever we teach it. Not kindergarten, but sometime around then, right? So it's exactly the same gravitational force. Now, and this story just kept going and going. Electricity and magnetism were realized to be different aspects of exactly the same phenomenon, that of electromagnetism. And something else that always happens is whenever you realize that things are different phenomena or different aspects of the same thing, once that understanding is reached, you also tend to find that lots of other phenomena that you thought had nothing to do with the first two actually come into the fold as well. In the case of gravity, Newton and Kepler before him and Galileo were motivated by understanding the orbits of the planets around the sun. And then there are always these oddball things like comets that no one could understand at all. Well, once the basic principles were understood, you could understand everything. Comets, the funny, irregular motions of the planets, and everything. In the case of electricity and magnetism, light, which was a third thing that seemed to have nothing to do with either one of those first two, was seen to be undulations of electric and magnetic fields. So there's many ways of characterizing this idea of unification, but one of them is that there's converging arrows of explanation for why questions. Okay? You ask why, and you find in the end, properly interpreted, the same answer to many, many different questions. So that was something that went through to the end of the 1800s, and the 20th century really pushed this program to another level, because while the earlier successes all involved rather familiar notions from the everyday life in the outside world that more or less everyone was familiar with, in the 20th century, we realized that this program pushed even further and started involving completely unfamiliar concepts, at least things that were unfamiliar to us as macroscopic lugs wandering around on the face of the planet. Okay? So, for example, Einstein taught us that space and time are different aspects of the same thing, and there's actually one unified object known as space-time. So we could actually mix space and time with each other. They seem to be completely different, and yet they're in some deep way subtly linked with each other. One of the consequences of that understanding was that a third thing, gravity, was associated with undulations in space-time. And that had a number of radical consequences. For example, we could start talking about and even conceptualizing what it would mean for a universe to be expanding. Okay? It's not, when we say that the universe is expanding, it isn't that it's expanding into anything. It's not like an explosion with things going out in some pre-existing bigger space. The universe is expanding because if this is a galaxy and that's a galaxy, and a little while later they're further apart from each other, it's because more space has been invented in between them, created out of nothing. And that's what's driving the distance between them further and further apart. That's something that you couldn't even conceive of if you didn't have this idea that there was a space-time and that it was a dynamical entity and it did stuff. Okay? Similarly, quantum mechanics did something even more radical. Einstein is the sort of most famous theorist of the probably ever, but it's not quite as appreciated as it should be, that the ideas of quantum mechanics are at least 10 times more revolutionary than those of special relativity. And that's why it took quantum mechanics wasn't invented by a lone genius sitting in a patent office, but it was the result of 25 years of 15 people working around the clock, themselves to exhaustion, figuring it out. It's a much, much more radical set of ideas. But one thing that it did, it unified the ideas of particles and waves. So we thought we had different phenomenon in nature, particle-like phenomenon, wave-like phenomenon. But we discovered that, in fact, there's no such thing as waves fundamentally at all. What we really have are particles. Everything's particles. But those particles don't obey the usual laws of classical physics. Sometimes they obey the laws of quantum mechanics. Sometimes large collections of those particles behave classically like particles. Sometimes large collections of those particles behave classically like waves, but really the underlying thing is fundamentally particles. And associated with that were a number of radical ideas, like the idea that, in fact, nature isn't exactly deterministic. There's the famous uncertainty principles. We can only predict probabilities for outcomes of measurements and so on. But again, it brought a unification. It made waves and particles the same thing and had a whole lot of ancillary consequences as well. So those were the big revolutions that brought us to the sort of 1930s, the early 1930s. And in a very broad brush, the next 50 years were all about putting these two revolutionary ideas together and seeing how they fit. One never knows ahead of time in physics whether it's time for radical ideas or for conservative ideas. Almost always it's time for conservative ideas. That's because ideas normally work. We understand things pretty well, and normally following your nose and finding the consequences of the ideas that you have already is the right thing to do. Only when you've done that enough that you've exhausted every other possibility do really, really radical ideas start making sense. So in fact, most of the second part of the 20th century, from the 30s on, the next 50 years or so, was really an ode to conservatism. And it was really trying to figure out how to take these ideas and put them together. Not throw everything out the window and start all over again whenever the going got tough, but to actually try to take the ideas seriously and synthesize and merge them. It's maybe a little ironic historical fact that the founders of quantum mechanics themselves, in attempting to synthesize quantum mechanics and relativity, ran into all sorts of what we now understand as essentially technical problems. But at the first drop of the hat, they were ready to abandon everything and say, we need another revolution. That's all they were ever used to, was revolution. And every trouble they had, they thought, oh, it's got to be revolution again. And they were just wrong. And ironically, the theoretical physicists who were famous from that era, most famously Richard Feynman, for example, didn't play the role of a crazy radical. He was a complete conservative. And it is a funny, strange fact that it was the youngsters who were much, much more conservative than their elders, and actually just said, no, we're just going to sit down and calculate and figure out how to put these things together. But it's a good thing that they did, because it was a long slog to figure out exactly how to put these two ideas together. We now know how to put these ideas together, and we know in some detail how to put them together. The synthesis of quantum mechanics and relativity is a big and very beautiful subject known as quantum field theory. And it's something that we learn more and more and more about even today. So it's not a closed subject. We still get surprises about unusual things that happen when we put quantum mechanics and relativity together. But we have the basic rubric, the basic building blocks, the basic theoretical structure is firmly in place and is a very solid foundation on which we can use to describe everything we see in nature so far. It has, of course, many, many aspects to it, but let me focus on one of them that's going to play a recurrent role in the rest of this talk, which is that putting together quantum mechanics and relativity forces and predicts the existence of antiparticles. So that if we have electrons and protons, there must be particles in nature with exactly the same properties, all exactly the same properties, exactly the same mass, everything exactly the same, except their charges are flipped. So there has to be an anti-electron or a positron, and similarly an antiproton. Okay? So this is really an amazing fact that the unification of space-time and quantum mechanics doubled the world. No one had seen these particles before. the early researchers who realized that this seemed to be a prediction of the equations of the theory were so dismayed by such an outlandish prediction that they did everything they could to make the prediction go away. Of course, it didn't go away. It kept sticking there. And of course, eventually, dutifully, the experimentalists found all of these antiparticles in cosmic rays at first, and now they're an everyday aspect of our life in high-energy physics. So this is a really startling fact. Putting together relativity and quantum mechanics doubles the world, and I just want to give you a flavor of why. Just a flavor of why. If this doesn't make any sense to you, just ignore it, and we'll go on in a second, but it might make sense to some of you. So something that many of you know, despite recent reports to the contrary from CERN, a subject that I will only talk about in the question period if asked, and if the questioner is prepared for a long rant. Things don't go faster than light, and one of the reasons is that Einstein tells us that if we have an event, if we have A, you fire an electron gun, and that electron is received at a later time by B, if this manages to go faster than light from A to B, then according to the rules of relativity, if we just move in a different reference frame relative to this one, just at some large velocity perhaps, we can reverse the time order between the events A and B. So it looks like before the electron gun was fired by A, there's an electron received by B. Okay? And that's why we're not allowed to send things faster than light. That's one of the reasons in relativity that's not allowed. We want to preserve a picture of causality. However, in quantum mechanics, something that you may also know is that we can't know the position and velocity of particles at exactly the same time. This is one of the famous facts about the Heisenberg uncertainty principle. And so that means there's always some chance that despite the fact that you thought you were pinging something here at A, that maybe you actually did a little further over, and the electron did manage to make it from A to B, maybe without really going faster than light, only appearing to go faster than light. But you're still left with a paradox. One way or another, you thought you turned something on at A, and it seems like there's some chance for it to be received in B before it was sent by A. So how can we deal with this situation? Well, the way to deal with the situation is to actually give a different causal picture for what actually happened here. Because really what happened is that there's some flow of charge forward in time from A towards B. And in this different reference frame, instead of thinking that this electron is moving backward in time, if you like, from A to B, you can think instead that there's a flow of positive charge forward in time from B to A. And that's the only way you can interpret what happened in a way that preserves causality. But for that to be possible, there has to be some particle out there with exactly the same properties as the electron, but with opposite charge. And that's why the synthesis of quantum mechanics and relativity requires antiparticles. There are some holes in this argument. But it's basically pretty close to the actually correct argument for why this has got to be the case. So quantum mechanics and relativity together imply the existence of antiparticles. And the existence of antiparticles has an immediate and very dramatic consequence. Something that we can't talk about without. If antiparticles didn't exist, this would not be the case. But again, we're just putting relativity and quantum mechanics together. You follow your nose and you discover something astonishing, that the vacuum is actually an exciting place. So the sort of story of the last 100 years has been that things that we thought of long ago as being static arenas, like space and time, themselves become part of the action. Space-time can curve and undulate and have something to do with gravity. This goes even further. Emptiness, the vacuum, empty space, is actually itself an arena for lots of exciting action. What do we mean by that? Well, let's say you try to verify that some region of space is empty. You'll do it by taking a handy-dandy magnifying glass. That's my picture of a magnifying glass, okay? And you look at some little region of space, trying to check that it's empty. Well, because of the uncertainty principle, if you're looking at a smaller and smaller region of space, you've got to put more and more energy into that region. But at some point, you put so much energy into that little region that nothing stops you from producing a particle and an antiparticle. There's energy to do it. Charge is conserved because the antiparticles have opposite charge. So absolutely nothing stops this from happening. And so your act of trying to verify that some region of space is empty actually produces particle and antiparticle pairs. And it just gets worse and worse as you go to shorter and shorter distances. Anything that's out there in nature, any particle and its anti-thing, can eventually be produced and seen by this act of magnification going to shorter and shorter distances. So if you had a picture from high school of an electron as this boring little point-like thing, maybe with like little lines of electric field going out of it. Because of quantum mechanics and relativity, the picture is much more exciting. We actually have, you can keep as a metaphor, as a mental picture, you can imagine that there's particles and antiparticles popping around all the time. At shorter distances, you'd get heavier particles and antiparticles, but there's this cloud of particles and antiparticles that are surrounding the electron at all times. And this is a metaphorical picture. It's useful to carry pictures around like this in your head because they allow you to get the correct answers to various questions that you might ask, such as, if you look at what's going on, will you see a particle and antiparticle? Yes, you will see them, and it's useful to think this way. It's useful to think that there's this cloud of particles and antiparticles surrounding the electron. I should say that people often call high-energy accelerators, like the LHC, the biggest microscopes, the most powerful microscopes in nature, in the sense that we're looking at very, very short distances. Okay? But if you're a microscopist, if you're a biologist, some serious microscope person, you'd ask, what is it looking at? And it's not like looking at a piece of hair or a leg of a frog or something like that. What is it actually looking at? And the answer is it's looking at the vacuum. What these high-energy accelerators are doing are taking snapshots of this roiling mass of particles and antiparticles that are going on in the vacuum all the time. And those snapshots, the shorter and shorter the length scales, the shorter and shorter the time intervals between the snapshots are, the higher and higher energy processes that we're talking about, the heavier and heavy particles out of the sea we can see. And the detailed properties of these things tell us a lot about the underlying laws of nature governing. All right. Okay, so all of these developments, this has sort of brought us to around the 1970s. It really took around this sort of 50 years for the theoretical physicists to get their act together and understand exactly how quantum mechanics and relativity could play together and have this solid theoretical foundation. But these developments culminated in 1970 with the invention of a specific quantum field theory, specific menu of particles and interactions that worked according to the laws of relativity and quantum mechanics, that describes all the known particles and interactions that we know of down to distances of at least around 10 to the minus 16 centimeters. Okay? This is prosaically we call the standard model of particle physics. We should have come up with a better name for such a great accomplishment. But anyway, it's not. So there's a general rubric of quantum field theories in general, but a specific theory involving electrons and quarks and other particles describes actually our observed universe. And it is spectacularly successful. So often you might see talks like this and get some impression that all we ever do is say these vague, mushy things about things popping in and out of the vacuum and so on. But rest assured, these are really, as I said, these are metaphors. But they're associated with some incredibly precise set of mathematical rules for how to calculate the answer to any question that you might like to ask. And the answer to some of those questions can be predicted theoretically to astonishing precision, and are also measured experimentally to astonishing precision. This is incidentally one of the kinds of measurements that are done beautifully and have been done beautifully at Brookhaven for many years. So here's an example. The electron can be thought of as a little spinning top, and the fact that it's this little spinning top gives it, and it has some charge, gives it some magnetic properties. But this cloud of particles and antiparticles that surrounds it affects that magnetic property in a very precise and calculable way. There's a deviation from its most naive value, which is this quantity. You don't need to know what it is exactly, g minus 2 over 2. And this is what it turns out to be. Okay, so you go out to 11 or 12 decimal places there. And I haven't bothered to write whether this is a theoretical result or an experimental result because they actually agree out to that many decimal places. Okay? There are a number of other consequences of this idea that there's this cloud of particles that surrounds anything. For example, the strength of the electromagnetic force changes very, very gradually as you penetrate this cloud of particles and antiparticles. And the way it changes as you go to shorter and shorter distances is something that's very precisely determinable, measurable, and is something that we've understood and seen. So these are not just pretty pictures. They're associated with a very powerful mathematical structure and machinery that allows us to make often astonishingly precise predictions. And they agree with the experiment. Now, this is, of course, the poster child for the best agreement between theory and experiment that we've seen. But there are other things. There are tens of thousands of other kinds of experimental observations where theory and experiment agree to a part in 100, a part in 1,000, a part in 10,000. Okay? So when I say it's spectacularly successful, this is a sort of standard of precision that we're talking about. Not only is this picture incredibly successful at agreeing with experiment, but it's done something conceptually very important. Those different forces that we talked about at the beginning, gravity, electromagnetism, weak, strong, they all look very, very different. They feel different. They seem different. For a long time, even through the 1960s, it was not at all clear how to even talk about them on an equal footing. And yet, what this structure, what the standard model does, is actually tell us that they're all described in exactly the same basic language. They're all described by this general theoretical structure that I mentioned. And more startlingly and more interestingly, the apparent big disparity between all these forces is actually a long-distance illusion. So, for example, the strong force seems like it's locked up permanently inside the nuclei, whereas electromagnetism acts at very, very large distances. Okay? Why is there this big difference? Well, it just turns out that it's a sort of a detailed difference between the interactions of electrons and photons, which has to do with electromagnetism, and the interactions between the particles that make up the proton, the quarks, as well as things that keep them inside the proton called gluons. The interactions between quarks and gluons are essentially identical to the interactions between electrons and photons. At very short distances, the rules that govern both of them are, apart from some not terribly important details, essentially the same. But how those rules play out at large distances radically changes what the world looks like at very big distances. For example, it turns out that the strength of the interaction, I told you a second ago that the strength of interaction, let's say between a pair of electrons, as you go to longer and longer distances, it gets very, very gradually weaker and weaker as you penetrate this cloud of electrons, of particles and antiparticles that surround the electron. Well, it turns out that for detailed reasons, exactly the opposite happens for quarks and gluons. So that the strength of the interaction between quarks and gluons grows very, very gradually as you go to larger and larger distances. But that means that eventually at some distance scale, it grows so large that it permanently traps the quarks and gluons inside protons and neutrons and other particles. So this apparently insurmountable difference between the strong interactions on the one side and electromagnetism on the other side is a complete long-distance illusion. At short distances, they're governed by essentially the same kinds of laws. Okay? This is the reason in this business, in fundamental physics, we want to go to short distances. Often, this kind of physics is characterized as trying to discover the ultimate building blocks of matter and things like that. Okay? That may be why some people are interested in studying high-energy physics. It's certainly not the reason I was interested, and I think many of my colleagues were also motivated by something else. We don't care so much about some strange zoo of particles. What we care about is the actual underlying laws that govern them. And what we've discovered over the last 100 years is that the essential unity and simplicity and beauty of these laws is obscured at long distances, but manifests itself at short distances. That's why we go to short distances. Not because we want to add to a zoo of particles that we've discovered already, we want to add 100 more to them. We will discover, hopefully we'll discover a whole slew of new particles, but it's not the particles themselves that we care about. You should think about the particles as the alphabet. There's a novel. We're actually interested in the story that those particles are telling us about the laws. And this is why we do it, because we've seen over and over again that it's at short distances that this unity becomes manifest. And it's obscured by what are, from the point of view of the fundamental equations, long-distance accidents. All right, so this is the theoretical structure that explains essentially everything that certainly all the physics that's relevant for everyday life around us, any basic question about the universe that you ask, it will have some answer in this theory, and we understand an enormous amount about it. There's one question which the theory has an answer to, but which we haven't yet verified directly by experiment. And that question has to do with the origin of mass. Well, the origin of some mass. So let's talk about a particle like the electron. The electron goes around the nucleus of the atom, but if the electron didn't have any mass, it would move around at the speed of light, and there would be no atoms, obviously, because it couldn't be trapped inside the atom. So you can ask a very basic question: why does the electron have a mass? And in this theoretical structure that we have, there is an answer to this question. As I said, there should be an answer to any question that you might like to ask. This is one question you might like to ask. And the nature of the answer is this is something that after many years of giving talks like this, I've still yet to find a good metaphor for this that doesn't do justice to what's actually that does justice to what's actually happening. But this is the best that I and I think many other people have come up with. The idea is to imagine that the universe is filled with a sort of fluid, or we call it a kind of a condensate. The reason one shouldn't use this analogy, I'm sorry I am, is that when you say this, people immediately say, wait a minute, that sounds just like the ether. And you idiots, didn't you learn anything? 100 years ago, you got rid of the ether, and now you're putting in an ether again. Well, the best I can say is it's some kind of something that fills the universe that's not like the ether. And it's true. It's not like the ether. It's not like the ether in the sense that observers moving at different velocities will see exactly the same properties of the condensate, unlike the ether. But anyway, I apologize. That's the best I can do right now. But the picture is that as the electron moves around, it bangs into this condensate. And it's this interaction with the condensate that prevents it from moving at the speed of light. Okay, and it's what gives it some inertia, and that's what we interpret in the end as its mass. So the electron bangs into this condensate, over some typical length scale. It travels a typical distance before it bangs into the condensate. It happens not to bang into it terribly strongly, which is why it has a relatively small mass compared to the other elementary particles. Other particles, less familiar in everyday life, things called top quarks, W and Z particles, and so on, interact with it much more strongly, and so they get a much larger mass. For very good reasons, the photon doesn't interact with it at all, and so it remains exactly massless. But there's a typical length scale between these collisions. Okay? In this theory, we have to, in order to agree with experiment, that there are some parameters. We have to choose these parameters, and one of these parameters is the effective length scale between these interactions. And that effective length scale turns out to be around 10 to the minus 17 centimeters. Okay? So remember I told you this number, 10 to the minus 17 centimeters, was a property of nature, okay? And this is a property of nature that it is. Electrons that move around bang into this condensate every 10 to the minus 17 centimeters or so, and that's why they have their inertia, okay? All the particles that we know get, particles like the electron, the tops, the W's and Z's and so on, bang into this condensate, but they all have this typical length scale around 10 to the minus 17 centimeters. So that's a number that's sort of hardwired into the laws of nature. People actually knew about this length scale, 10 to the minus 17 centimeters, for a long time. People have known something is going on at these distances for around 70 years. So I say it for the second or third time. One of the things that's exciting about the particular epoch that we're in right now is that we're about to probe physics at this distance scale. And we're going to figure out exactly what happens when these particles bang into this condensate. Okay? Thereby, we're going to learn something in a lot more detail about the precise way in which this mechanism works, and things like electrons can have a mass and atoms can exist and so on. Okay. So one of the things that simply must happen is, and this is a general consequence of general principles of quantum mechanics, is that the collisions at high-energy accelerators like the LHC, because we're probing distances of around 10 to the minus 17 centimeters, we'll put wiggles in this condensate around 10 to the minus 17 centimeters. Those wiggles will propagate out of the places where the collisions took place and will be interpreted as particles. So the wiggles on top of this condensate are particles, And the famous Higgs particle is, in fact, the name we give to the excitations around this condensate. So again, we care about the Higgs particle not so much because it's some random new particle, but because it's associated with this with this fundamental question of the origin of the inertia of particles like the electron, ultimately. Now, that's something which in the current theoretical structure there's a beautiful theory for. So the properties of this Higgs, if the theory is correct, are very well known. It's something that we can look for, and we'll come back to it towards the end of the talk. But it's something which has not yet been directly verified by experiment and is really the first order of business at the LHC. All right. So that's a summary of where we had gotten to, and I now want to spend the rest of the talk telling you about what some of the problems are and how we're going to use the LHC to learn something about them. Well, I'm not going to spend too long on this problem, other than to just tell you a little bit about it. But it is one of the major conceptual problems that we face. And that's this first question. Space-time is doomed, so what replaces it? If we go back to this picture of the length scales, this was a question that had to do with this very, very tiny distance around 10 to the minus 33 centimeters. Okay? And one way of understanding why there is what this 10 to the minus 33 centimeters is if we look at the electric force and the gravitational force between a pair of electrons. The force between the pair of electrons is, the electric repulsion is 10 to the 42 times stronger than the gravitational attraction between them. Gravity is a stunningly, stunningly weak force compared to everything else. There's a variety of ways of saying that precisely, which this slide is doing, which I won't go into. But it's a stunningly, stunningly weak force. And now you might think that both electricity and gravity are inverse square force laws, so that the actual ratio of the strength between the forces doesn't depend on how far apart they are. Okay? But actually something new starts happening as you take this pair of electrons and you start trying to push them closer and closer together at distances less than, it turns out, around 10 to the minus 11 centimeters. What happens is, again, this darn uncertainty principle hits you over and over again. You've got to put more and more energy to hold these electrons closer and closer together, right? But as you do that, that energy by E equals mc squared has some effective mass, and that mass gravitates. So the actual force of gravity between this pair of electrons starts getting stronger, even though the electric force is staying the same. As you push them closer and closer together, the actual force of gravity between them starts getting stronger. So now something exciting is going to happen, because as you go to shorter and shorter distances, at some point the gravitational force will catch up with the electromagnetic force. And that distance scale is around 10 to the minus 33 centimeters. Okay? It's a shockingly, shockingly small distance scale. It's 17 orders of magnitude smaller even than the distance we're going to go to at the LHC. And its very tininess is a reflection of how weak gravity is compared to the other forces. Okay? But nonetheless, just extrapolating what we know, following our noses, we find that the gravity becomes very, very strong at 10 to the minus 33 centimeters. And it's actually the strongest of all the forces at 10 to the minus 33 centimeters. And more disturbingly, if I use my magnifying glass again, and I try to probe any kind of physics, any distances and times, anything that start to approach 10 to the minus 33 centimeters, I find I have to put so much energy into such a tiny region of space, again by the uncertainty principle, that I can no longer neglect the fact that there's a huge amount of mass in this small amount of space, and that mass is actually going to collapse the region I was trying to look at into a black hole. So we're trying to probe what's going on at really tiny distances, but we're stymied by the fact that the uncertainty principle forces us to put so much energy into such a small region of space that we collapse that region into a black hole. That means that there's no operational meaning. There's no experiment you can devise, nothing you can do that can measure distances and times smaller than 10 to the minus 33 centimeters, 10 to the minus 43 seconds, and so on. And this simple thought experiment, together with a number of more subtle thought experiments of a similar nature, strongly suggests that there's no such thing as space-time fundamentally. Every time this has happened to us in physics before, that there's some notion that we can't even in principle precisely define, in this case it's space and time, it means that those notions are gone and they have to be replaced by something more primitive. But that's very startling because the thing that we're getting rid of here is space and time itself. Right. And this shows up in a variety of places. It shows up as we get close to the Big Bang, for example, or it shows up near the center of black holes. And what happens here is simply that we have wonderfully successful theories, and those theories predict their own demise. They just break down. Simply break down as we get to these very, very extreme places. For example, often people ask what came before the Big Bang. The question is ill-posed, because as we approach the Big Bang, the very notion of space and time are breaking down, the notion of time in particular is breaking down, the notion of before is breaking down. It has to be replaced with something radically different. We don't even have the grammar for it yet. We don't have the correct conceptual structure to even talk about it. So the sort of question, what came before the Big Bang, is a classic kind of sentence that you can say in the English language, but which is meaningless in physics. We know there are many other sentences like that. For example, what is the position and velocity of this electron? That's also a question we can state in the English language, but which we now precisely know is simply an unallowed question in physics. Simply, it's very likely that the question, what came before the Big Bang, is a similarly unallowed question. And the challenge is to figure out what the allowed questions are and what the correct conceptual framework is for talking about this. Okay, so this is the big problem. Probably the best idea that people have come up with for attacking this problem is string theory. I won't have time to talk about it, other than just to tell you, if you haven't seen this before, you won't understand it from the slide, but just to take home a slogan. 20 years ago, people thought there were different parts of theoretical physics. There are string theorists, there are people who studied particles and forces, and we now understand that string theory is just another way of talking about good old-fashioned quantum field theory and good old-fashioned particle physics. And they're actually totally unified with each other in a very striking and remarkable way that I don't have any real time to talk about. But this is really the slogan, is that theories of quantum gravity and quantum field theory are very intimately related to each other. And so now there aren't different camps in theoretical physics anymore. Well, there is a small camp of people with bad ideas, but the set of all good ideas... no, this is a serious comment. The set of all good ideas that have ever worked are really seem to be different aspects of the same thing. So there is no sort of intellectual clash between different parts of the subject anymore. Okay, but and one of the things that these developments have done is give very concrete notion to this idea of emergent spacetime. We've understood how spacetime can emerge from more primitive notions, but actually, what we've really understood is how space and gravity and strings and all this other stuff can emerge from more primitive notions, but we've not understood how time can emerge from more primitive notions. And this is probably one of the central conceptual obstacles of the 21st century. It's related to lots of deep, confusing questions in cosmology and so on. So that's a very brief summary of the first set of questions. In a very interesting tangential way, even this set of questions could be related to the LHC. I probably won't have time to describe it unless people ask me in questions. But I did want to tell you about it, because this is indeed one of the central questions that we confront in this century. The next set of questions has to do with this very basic question. Why is there a big universe? The universe is big, even though the laws that govern it are quantum mechanical laws that operate on the very, very smallest scales. And so again, it's back to this question. We had these three basic scales: the size of the universe, the weak length, and this Planck length. There are these enormous separations between them. Why are there are these big separations? And the reason this is very puzzling goes back yet again to this feature of this union of relativity and quantum mechanics, that there's antiparticles. That means the vacuum is exciting. Okay? I went through that whole song and dance at the beginning just so you can see how it's the same issue over and over again. It's this excitingness of the vacuum, which in the presence of gravity leads to the breakdown of space-time near the Planck length. And as we'll now see, also seems to make it impossible or wildly implausible for there to be a big macroscopic universe. And yet, we do comfortably live in a big macroscopic universe. So the vacuum is exciting. There are all these particles and antiparticles popping in and out everywhere. But the problem is that it's way too exciting. Much, much too exciting. At least intuitively, if we imagine that we have a sort of a big box There are some fluctuations. According to the uncertainty principle, there are some fluctuations, and as we make the box smaller and smaller, the energy in these fluctuations gets bigger and bigger. That's, again, the basic feature of this of the uncertainty principle. But that means that if I make the box even smaller, it's a smaller box, so the energy in those fluctuations is even bigger. Even smaller still, the box is even smaller, the energy is even bigger. So if I look at the energy per volume, that's starting to get enormous. Just the energy in these quantum fluctuations of the vacuum seem to be absolutely enormous. So we can do a little estimate. Just because of these quantum mechanical fluctuations, there should be some energy density just in the vacuum. How big is it? Well, it's some energy divided by some volume. And we're going to do a little calculation here. Fortunately, we don't actually have to do anything because words just really suffice in this case. I seem to be able to make this energy as big as I want. By making the box smaller and smaller, I seem to be able to make the energy bigger and bigger. But I just told you that we actually can't even talk about space and time at distances smaller than this Planck length. So let's do an estimate. Let's see what this size would be right around the Planck length. Let's say it's a Planckian energy divided by a Planckian volume. So that's how big the energy density should be. That's a back-of-the-envelope estimate. Any theoretical physicist worth their salt can estimate anything on the back of the envelope and get the answer right to a factor of 10. If they're really good, they can get it right to a factor of 3. But anyway, so we're doing such a back-of-the-envelope estimate now. Okay? So it's a Planck energy per Planck volume. Now, what does this energy density in the vacuum do? If there was no gravity in the world, it would do nothing. But with gravity, it's going to do something. Remember, energy and mass curves space and time. And so this energy density in the vacuum is also going to curve space-time. How could it curve it? Well, it's got to make it do something. So for example, the universe could expand. Okay? But what is the rate at which it would expand? What's the number that would be associated with that? We actually don't have to do any calculations because every single word on the slide is Planck. It's a Planckian energy of a Planckian volume. Gravity is associated with the Planck scale. So the only number that could possibly come out is some Planckian time. That means that this estimate for the energy of the vacuum would lead us to predict that the universe is explosively accelerating, for example, doubling in size every 10 to the minus 43 seconds. Or it's curled up on scales that are around 10 to the minus 33 centimeters. And that's just what we get out of this back-of-the-envelope estimate. That's just wildly wrong. Wildly, wildly wrong. In fact, the situation is worse than that. We've discovered the universe is accelerating. It was this year's Nobel Prize in Physics, richly deserved for this incredible discovery that the universe is actually accelerating. But it's doubling in size every 10 billion years, not every 10 to the minus 43 seconds. So we have this gigantic discrepancy between back-of-the-envelope estimate and reality. And I remind you that this is the same group of people, it's the same theoretical physicists who in other places do calculations that agree between theory and experiment to 12 decimal places. So we're not a bunch of yahoos who are always wrong. We're actually used to being right to stunning precision. So when we're this wrong, we really take it personally. Okay? I used to call this the biggest error of a back-of-the-envelope estimate relative to the right answer in the history of physics. But then I realized I don't think anyone else has screwed up remotely this badly. So I think, in fairness, we shouldn't insult any of the other sciences. It's the biggest error or difference between the back-of-the-envelope estimate and the right answer in the history of science. Now, I told you we have this whiz-bang, fantastic theoretical structure that agrees with everything. Any question you ask about the world, it has an answer. So here's a very simple question. Why is the universe big? So we should have an answer to that. Yes, we do have an answer. We definitely have an answer. We'd better be able to answer that before we go on and calculate all these other things to 12 decimal places, right? So what do? Well, we say, good, this quantity, this is the energy density of the vacuum. It's called lambda. We say that its observed value there is this quantum correction to it from all these quantum fluctuations. And let's say in some units, like Planck units, you spend many, many graduate student hours, and someone calculates that it's 2.6493781, and you really push them hard, and they work to 120 decimal places, and they even to the 121st decimal place, and they work it out. They're exhausted, but they've worked it out. There it is. Okay? What we do is say, oh, thank you very much, graduate student. So what must be going on is that there was a piece that was sitting there already before these quantum corrections whose size was negative 2.6493781 ... And they agree to the first 120 decimal places, and then they start disagreeing in the 121st decimal place. Okay? They better disagree because this residual tiny amount is what we think is driving the acceleration of the universe today. So that's what we actually do. Nothing stops us from doing it. We can do this. And once we do this, we accommodate, I think you'd say we don't explain, but we accommodate why there is the big universe. Okay? And then we can go on to make all these other wonderful, accurate predictions. But this just looks ridiculous. Okay? And it's like walking into a room and seeing a pencil standing on its tip on a table to an accuracy of 1 part in 10 to the 120 degrees from vertical. Okay? It could be. It's a possible consistent arrangement of a pencil. But if you saw it, you might be confused. You might look for a string. Is there a string? Is it hanging from a string? Or is there a little hand holding it up? What's going on? Why is it sitting there so vertically? You might look for a mechanism. But this is what we have to do. In the current theory, it just looks like it's sitting on its tip. Okay? And this is our answer to the question, why is the universe big? Not a great answer, I think you'd agree. There's a very similar issue associated with the question of why gravity is so weak compared to all the other forces. Remember I told you as the electron goes along, it bangs into this condensate. Well, it's the same story over and over again. Violent quantum mechanical fluctuations at shorter and shorter distances, bigger and bigger ones at shorter and shorter distances, would lead you to suspect that the electron bangs into this condensate just because the condensate is fluctuating so much. It bangs into it not every 10 to the minus 17 centimeters, but every Planck length or so, every 10 to the minus 33 centimeters or so. Okay? That's what you'd expect, and that's what you get from a back-of-the-envelope estimate. If that happened, all the particles would be 17 orders of magnitude heavier. You and I would collapse into black holes. It would be a horrible world. There would be no love, and that's what it would naively be. And what we have to do again is take two parameters and finally adjust them to an accuracy of 1 part in 10 to the 30 rather than 1 part in 10 to the 120, but it's still plenty horrible. Okay? And that's our current answer to this question. Why is gravity weak? Okay? Both of these questions boil down to the same thing. How can there be, in a world with violent short-distance quantum mechanical fluctuations, any kind of long-distance order of any sort? Okay? And it's just an immediate consequence of all the good things that we think work about putting relativity and quantum mechanics together. Okay? So that's why these are such important paradoxes, because they spring from a deep and simple origin, and they're so big that they make us think we're missing some extremely radical or some big new ideas anyway, to explain such apparently simple questions about the world around us. Okay? So I've said this already. And again, if these tunings didn't happen, the universe would be incredibly unpleasant. Okay, so I'll probably just take another 10 or 15 minutes, and then I'll end. If we go back to this argument and try to imagine what could it be, this is such a big problem, something needs to solve it. What could it be? From the way I set it up, it should be clear that the problem is deeply tied to this union of space-time and quantum mechanics, and this problem of antiparticles and the fluctuation and all of it. So it stands to reason that any resolution to these problems can't just monkey with things in some random kind of trivial way, but has to do something more profound to the structure of the theories themselves. And a good hallmark of important problems in theoretical physics is how hard they fight back, how easy it is to come up with even candidate solutions to them. These problems people have been thinking about for around 30 years, and there are very few candidate solutions to them. Very, very few candidate solutions to them. And all the candidate solutions involve some kind of radical change to our notion of space-time in one way or another. There's always some language in which this picture involves an extension to our notion of space-time. But if we want to solve this problem, here we have these big fluctuations. It's getting smaller, smaller, smaller. If we want to, for example, explain why the electron doesn't bump into this condensate every 10 to the minus 33 centimeters or so, something has got to change in the rules of the game. As this box shrinks to around 10 to the minus 17 centimeters, something new needs to happen there. If nothing new happens there, we keep shrinking the box, and the fluctuations are just going to get bigger and bigger, and we haven't solved the problem. So something new has got to happen here. Okay? This is a very important argument. It's, because it tells us that not only is this 10 to the minus 17 centimeter scale some important length scale that we've known about for a long time associated with this bumping into the condensate, but also something new has got to happen there, something that changes these rules in some important way, which solves the problem. And that something new is likely going to be some sort of extension to our notion of space-time. Okay? There's actually a historical analogy which is very helpful for this, which is a problem that classical physicists struggled with in the late 1800s. In the late 1800s, they looked at an electron. The electron is surrounded by some electric field, but you can just classically calculate the energy that's stored in that electric field, and you find that the energy is infinitely big. And it doesn't make any sense, because then the electron wouldn't be able to move around, it would have some infinite inertia. So something new had to happen, and they calculated that something new needed to happen by around 10 to the minus 13 centimeters or so. Well, something new did happen. It wasn't at all what they expected, which was that the electron was like a little sphere of finite size or something like that. It was much more radical than that. What happened was that the world wasn't classical anymore. There was quantum mechanics and relativity and all the rest of that wonderful stuff. There was this picture of this cloud of electrons and positrons, for example, surrounding this electron, that completely changed this point-like picture of the electron to this cloud-like picture at a distance of around 10 to the minus 11 centimeters. So their argument was essentially right. Something new did have to happen. It's just the new thing wasn't what they expected. It was relativity and quantum mechanics and all the rest of it, and it kicked in a lot earlier than they anticipated as well, at around 10 to the minus 11 centimeters. But this sort of argument has been used before and has been worked before a number of times. Actually, in addition to this example, there's two examples from just the last century where very similar kinds of problems arose, and they have a similar sort of solution. Okay, so if we go back here, what could it be? Well, it could be what we need if we want to understand how this is happening is some kind of extension to our notion of space-time that's going to remove these big violent quantum fluctuations and then make it natural for the electron to just bump into this condensate every 10 to the minus 17 centimeters or so. So it is like looking for a little hand that's holding up the pencil. We're looking for a mechanism that stabilizes it. There have been a number of ideas that both ideas involve some notion of an extra dimension of space. There's the sort of normal extra dimensions, and there's something known as supersymmetry. Now, somehow I find that normal extra dimensions get a lot more popular press. And it's something, I think, which is it's very vivid. You have this picture. There's this other space out there and so on. And it's certainly a subject I've worked on, a number of people have worked on. But I want to stress something. Extra dimensions are not a very deep conceptual idea. They're interesting. They're fun. They might be there, but they're not particularly deep. This is a much, much deeper set of ideas. Supersymmetry is a different kind of extra dimension and is a much deeper set of ideas that goes more deeply into the structure of space and time itself. So I want to just tell you a little bit about it and then transition to telling you about how the LHC is going to address these questions. So the idea is that in addition to our ordinary dimensions, there are some extra dimensions. But unlike these boring extra dimensions that get all the press, these extra dimensions have the feature that you don't measure distances in this extra dimension with ordinary numbers. You know, in the other kinds of dimensions, which are like a little, in addition to our space, there's some other circles or something like that. You just measure the distances in those dimensions with meters too. They're ordinary numbers. In supersymmetry, these extra dimensions are not measured by ordinary numbers. They're measured by some kind of quantum mechanical counterpart to ordinary numbers. So you'd measure the distance in this x quantum direction or the y quantum direction by some funny numbers that have the property that the product of the two of the numbers, normally a times b is equal to b times a. In this case, a times b is equal to negative b times a. So it's a funny kind of different rules for multiplication of these numbers. So it's our dimensions measured in meters and these quantum partner dimensions measured in these funny variables. Okay? This rule that a times b equals negative b times a has a consequence that a times a has got to equal 0. Okay? So there is so in fact the distances squared are just equal to 0. And that has an intuitive consequence that you can't take many steps in this extra direction. You can take one step, but if you take 2 steps, you're dead. You can at most take one step in this extra space. And so here we are. You have an electron moving around, but it can take a step into the extra space, and it will look, from our point of view, again, like a particle with much the same properties as the electron. Its magnetic properties will be a little different, but it's called the superpartner of the electron. Okay? So again, if supersymmetry is correct, there's a doubling of the world, much like the doubling we had when we went from particles to particles and antiparticles. And so here it is. So we have electrons and the superpartner called selectrons, and they have, the important point is there's actually a complete symmetry between what's going on in the ordinary space and what's going on in this quantum space. So that if we have an interaction between an electron, and a photon, it's exactly the same as the interaction. The strength is exactly the same as the interaction, for example, between an electron and something where the electron and the photon take one step in the quantum dimensions, in which case they're called a selectron and a photino. Please don't blame me for these words like squark and photino. This was the 1970s, and you know as much about it as I do. So, but anyway, the important point is that there is a complete symmetry between the ordinary and these quantum dimensions. And so how does that solve our problem? That solves our problem in a very dramatic way. Something had to change with these rules. As we go to shorter and shorter distances, there are these more and more violent quantum fluctuations. Something has got to give. What gives in this picture? What gives is that as you get to distances shorter than 10 to the minus 17 centimeters, you start being able to see these quantum dimensions. Okay? And then it's at shorter distances than that, then this perfect symmetry between the two of them starts becoming established. Now, you would want to have these big, big fluctuations inside the ordinary dimensions as you go to shorter distances. But you know you can't have big fluctuations in the quantum dimensions. You can't even take more than one step. You can take 2 steps and you're dead. There's no fluctuation of any sort allowed in the quantum direction. So how is this possible? We have to have a complete symmetry between our dimensions and the other dimensions. The only way this is possible is, in fact, if these quantum fluctuations in our dimensions stop. We don't fluctuate anymore. Okay? What was needed was some extension to the picture of space-time. This is an extension to the picture of space-time, and this is how it solves the problem. And what I've told you is it's still a little bit of a metaphor, but it's 90% of the way to the correct technical explanation for how this actually works. Okay? It really is directly hardwired into this extension of our notion of space-time that you remove violent quantum fluctuations and make it possible for a macroscopic universe to exist. So supersymmetry is something that helps quantum mechanics be consistent with the existence of a macroscopic universe. Okay? And it's a very deep idea for that reason. It's the only idea that we know of that actually accomplishes that for everything. Okay? I won't have time to talk about dark matter, so I won't say that. Okay? And I probably won't say this either. Well, let me just say one thing. We have had for a number of years some wonderful circumstantial evidence, really for 20 years or so, some circumstantial evidence that this idea of supersymmetry is on the right track. Remember I told you that the strengths of the interactions gradually change as you go to shorter and shorter distances. If we take the standard theory that we know and love, the strength of what I call in quotation marks the electromagnetic force, the weak force, and the strong force, which are now described in the same basic language, but still there's different numbers that goes with those strengths. Those different numbers differ by about a factor of 10. And if you just see what they look like as you go to shorter distances, you get a picture like this. They're kind of interesting. They seem to converge slowly to a common value, but not in any sort of great precision. They kind of converge, but they don't sort of quite meet. Okay? That's just what happens if you take our standard picture of the world. But for these reasons that I've told you already, we expect to see something like supersymmetry at around 10 to the minus 17 centimeters. And if we add these superpartners to the rules, something astonishing happens. We still follow the strengths of these interactions, and now we find that they merge to a point, to an accuracy of better than 1%. Okay? This did not remotely have to happen. It was not engineered to make this happen. This whole picture was devised to solve these other problems that I told you about, and yet one of the wonderful consequences is this picture of the unification of all the forces. Okay? Really remarkably, the place where they unify is also really close to this Planck length. It's not exactly there, but it's within shouting distance of the Planck length. It's around 10 to the minus 30, 10 to the minus 31 centimeters. Again, you often know in physics you're on the right track when things are not too hard. You do the most natural thing and it works. Einstein struggled for 30 years to come up with some sort of unification between electromagnetism and gravity and got nowhere. But we follow our nose with the ideas that we have, try to solve the problems that we have, and these things fall in our lap. This did not have to happen, and strongly suggests there is something to this, to a notion of a supersymmetric unification, not only between the strong, weak, and electromagnetic forces, but also perhaps with gravity as well, which isn't far behind. Okay, I won't have time to talk about the Copernican revolution. There is a major fly in the ointment when it comes. You notice that I talked a lot about this problem of why gravity is weak, and I talked very little about the even bigger problem of why the universe is so big. The first problem that we addressed, that problem of why the universe is so big, it turns out we don't have any good mechanistic explanation for it. All these years that people have thought about it, there's no good mechanistic explanation for it. There's a completely orthogonal sort of explanation, which is anathema to many physicists, but is at least a scientific explanation, which invokes a change in our picture of space-time, not at small scales, but at enormously large distance scales. I might as well say it. Okay. So the picture is the following, that we look out and the universe seems pretty much the same from place to place to place. But it could be that if we zoom way, 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 way out on enormous, enormous length scales compared to the observable size of the universe, that we'll see that it's an incredibly inhomogeneous place and differs from place to place. And that in fact, and this is a natural consequence of some of the best theories we have in cosmology, together with some natural ingredients in string theory. So there's a reasonably solid theoretical foundation for this, although it's not as solid as we'd like. But still, it begins to be possible to imagine a picture where on enormous, enormous distances, the universe varies wildly from place to place. There's one underlying theory, but there's lots of different ways that it's being expressed at large distances. And in those places, this value of the vacuum energy changes from place to place to place. Now, remember I told you we had to have this conspiracy of 1 part in 10 to the 120 in order to be able to find the vacuum energy with the value that we had. But imagine that there's 10 to the 1,000 of these places. Okay? There's 10 to the 1,000 of these places where the volume of the vacuum energy is different from place to place to place. Well, in the vast majority of these places, this fine cancellation won't happen. What will happen in those places is that the universe will be explosively expanding every 10 to the minus 43 seconds or so. And that's fine. That's a perfectly fine part of the universe, but clearly nothing can possibly exist there. And I'm not talking about intelligent life or anything like that. I mean, nothing. No structure of any sort. Everything is ripped apart, totally ripped apart by the violent expansion of the universe. So from this bird's eye view, there could be only a very few places out there where the universe just happens to be expanding slowly enough that any kind of structure of any sort can form. And so it's not surprising that we're going to find ourselves in those pockets of this sort of big multiverse. So there's this very, very, very big place. Most of it is totally lethal, and only in a very, very few places can we actually exist. Okay? This is, so far, the only scientific explanation we've come up with for the smallness of this value of the vacuum energy. And as I said, it's radically different than any sort of explanation we've had to use before in physics, which is why it's a very controversial subject. But it is the best explanation we have so far. And so it does open up this, as I said, this other extension of our picture of space-time. Could it be that we're actually a tiny part of a vast multiverse? And if it's true, it's the modern analog of the Copernican revolution. But there's lots of non-polemic, non-philosophical, actual physics problems that need to be solved. In particular, there's a conceptual problem of how we make sense of all these other universes if we can't actually directly see them. So there's lots, even theoretically, to be understood about this proposal. All right. So that reviews the entire theoretical situation to this point, and I want to spend the last 10 minutes or so telling you about how the LHC will impact this. So sorry it's going on a little long. All right. So that's the aerial picture outside Geneva. There's the Swiss-French Alps in the background. There's Lake Geneva. I think that's the airport. And of course, from the air, you don't see this big red ring on the ground. But 300 feet beneath where that oval is a tunnel and there's a beam, and we have beams of protons circling one way around the tunnel, and other beams of protons circling the other way around the tunnel, and at a number of places on the circumference, they're brought into collision with each other. Okay? So that's what it looks like inside the tunnel. You can barely make out the curvature, but you can see it. It's 27 kilometers around. It's a gigantic thing. It's every word associated with the LHC is some superlative associated with it. It's the largest experiment in human history. There's at least for the part that I'm talking about, there's 2 different collaborations, each roughly of 3,000 people each, working on this physics. It's truly international in scope, and of course the U.S. has a big stake in it. And there'll be a few fancy slides, but this is my slide telling you about what's going on. So these beams of protons are accelerated each to around 0.999999 times the speed of light. Okay? So that's 7 nines. So one set is accelerated that way, another set is accelerated the other way, and they're brought into collision with each other. Okay? So when they collide with each other, these very, very enormous energies are chosen so that when they collide, they're probing distances of around 10 to the minus 17 centimeters. Now, each proton here, if I take my magnifying glass and look at the proton, each proton is actually, you should think of it as a messy bag that's made out of quarks and held together with gluons. So most of the time, what happens when these 2 protons hit each other is, well, you would expect would happen if you take 2 messy bags of particles and collide them with each other. They just break apart and splatter in the direction that they're moving in. So the vast majority of time what happens is they just splatter into a big spray of particles, and because they're moving so quickly, the first spray goes mostly that way and the second spray goes mostly that way. That's what happens the vast majority of the time, and we're not interested in that. Or in this talk, we're not interested in that. Some people are interested in even that, which is also interesting. But we're interested in probing the laws of physics at very short distances. And so what we really are interested in is what happens when one of these quarks and gluons has a head-on collision with another one of these quarks and gluons in there. That happens much, much more rarely, like a millionth of the time that happens. But you know it's happened. You have a handle on when it's happened, because when they suffer a head-on collision, the results of what happens to that collision can come out at very big angles relative to the beam. They're not just getting blasted down in the direction that the protons were coming in to begin with. And so something new happens here. Something new happens, and we make a bunch of new particles. Now, these particles don't come out with name tags saying, I'm a new particle. They actually typically rapidly disintegrate in a time scale of order 10 to the minus 27 seconds. That's roughly how long it takes light to travel a distance of 10 to the minus 17 centimeters. And they decay to good old-fashioned particles that we know and love. Electrons, muons, they can decay into quarks. Actually, we don't see the quarks freely, but they pick up a lot of friends from the vacuum and turn into something called a jet. So what we have to do is then measure everything that comes out with the hopes of learning something about the story of what was going on in this original collision. Now, because these energies are so enormous coming in, the energies of the particles coming out are also enormous. And amongst other things, to be able to study them, especially particles like the muon, you have to stop them. Just stop them so you can see what they're doing. And you have to stop them by using just huge amounts of actual material to stop these very, very energetic particles coming out. And this is why what we do, and the we here is not a crappy theorist like me, but are the royal experimentalists who are the star of the show now. So we surround these interaction regions with gigantic detectors. And one of the reasons the detectors are gigantic is because the particles are screaming out with such high energies. It's one of the real ironies of this business. The LHC is the machine that's probing the very tiniest distances we've ever probed. So why is it the biggest machine we've ever made? And why are these detectors so damn big? And it's the uncertainty principle over and over and over again. We need these huge energies to probe tiny distances. And when we do that, the particles come screaming out with big energies. And just to stop them, we need these gigantic detectors that surround the regions. Okay? So this is what... this is one of the detectors, the Atlas detector. And when I say gigantic, I mean gigantic. It's 45 meters long, 24 meters tall. Always in these pictures, there is European issue people to like show you what people look like in this picture. And you don't need to go through, not going to go through any of this in great detail. But just so you get an idea, there's an onion-like structure that surrounds the interaction region. So one of the beams of protons is coming in that way, the other one is coming in that way. They bang into each other here, and a whole spray of stuff comes out. And when we surround it with these onion-like structures in order to just capture everything that comes out and characterize it as accurately as possible so we can figure out what was going on. So this is just like, it's a simulation of what actually happens. Oh, no, sorry, this is not a simulation. This is actually a real collision. With a beam coming in, you get a whole mess of spray of particles coming out. They light up the detector in different ways, and we use that to reconstruct and get a feeling for what actually happened. This is another picture of the Atlas detector with another European issue person. Okay, so these are like truly colossal and incredible things. They're really awe-inspiring things when you see them. Of course, fortunately, it's not. I mean, they're all sealed up now, but there was a nice time when you could see them as they were being put together. This is the other detector, CMS. It's a compact muon solenoid. The compact is because it's so much smaller than the Atlas. Okay, and there's another person. So it's a little bit smaller than Atlas. And every little bit of this, there could be hours of a colloquium on the or of a talk on the amazing intricacies of this machine. Let me just focus right in, for example, at very, very tiny distances, or one of the first things that happens closest in here are a lot of strips of silicon that are used to just to get a very good idea of the positions of charged particles as they come out of this interaction region. It's exactly the same principle as you use in your digital camera. But it's just a very, very fancy digital camera. It's okay. But there are all these beautiful strips of silicon really, really close in. So, we're talking about structures from the centimeter scale all the way up to the 40-meter scale, and every component has been carefully thought out and planned in order to extract as much information as we can. Okay? And, of course, they're gigantic things, so they're housed in huge caverns. This is a picture of the CMS cavern before the detector was lowered into it. And, in another talk, I could show you 10 images of how slowly they managed to, drop this thing down there very, very slowly and carefully. You have to worry about things like, by the time it's sitting on the ground, it has to be perfectly symmetrical. But it's going to sag a little bit under its own weight by millimeters. So you have to engineer it so it's a little bit oblate by millimeters, so when it sags into perfect shape. Okay, so these tens of meters objects are engineered to millimeter accuracy in order to get the physics we need out of it. Okay, and of course the very big news is that the LHC is running. It's running after, I used to give talks like this for 10 years, and it would always be that it was coming in 5 years, coming in 5 years. It was always coming in 5 years, and it's just incredible now that it's actually happening, and it's in full swing. Maybe the most exciting thing to most of us, especially theorists, also experimentalists, but even to a theorist, is that both the machine and the detector performance is just spectacular. Everything is working better than we expected at this point. Something else which is just a good qualitative thing to know about the LHC is that the LHC is the dominant producer of information on the planet. Okay? Every one of these events you have to store. Every one of these things, there's a gigantic amount of data that has got to be stored. It's roughly a terabyte a second. That's 10, I didn't even know what this unit was until I looked it up. It's 10 zettabytes per year. Okay? And in order to calibrate this, the total amount of all the other information on the planet that's processed in a year, all the Google database, everything, is roughly also around 10 zettabytes a year. Okay? So the information producer of the LHC is competitive with all the other information stored on the planet. Okay? So amongst other things, it's not only this engineering marvel, it's also a computational marvel. All right, but let's come back to the physics. So what do we want to do with this spectacular machine? Well, one of the, if there are solutions to some of these deep problems, then, for example, if there is supersymmetry, then it should show up at the LHC. For example, if we collide these protons, two of the quarks inside the proton could bang into each other with sufficiently high energy to kick themselves off into the quantum dimensions. So they would look like the superpartners, the squarks in our ordinary 4 dimensions. And again, they don't come out wearing a name tag saying, I'm a squark. This squark will decay, for example, to a quark and the superpartner of the photon called a photino. On the other side, it could decay in a more complicated way. So there's a whole chain and interesting cascade of decays that take place, all within around 10 to the minus 27 centimeters, all within 10 to the minus 27 seconds or so. And so what we see instead are these visible particles that come out and are trapped by the detector. Actually, in this picture, I've highlighted this photino here and there because this is a particle that turns out it's neutral, it's heavy, but it's neutral, and it has very weak interactions with everything else. So all these guys are visible to the detector, but these guys, the superpartner of light, superpartner of the photon, escapes. Just sails out of the detector. Don't worry, it doesn't do any damage on its way out, but it's not caught. It's not directly captured by the detector. So one of the qualitative things that we look for is events, to see if something like supersymmetry is going on, is events where lots of normal, visible energy and momentum are coming out, but there's something missing. There's something missing that doesn't conserve energy and momentum that allows us to infer the existence of something. So this is not an actual event. If it was, we'd be very excited. But it's a simulation of what supersymmetry would look like at Atlas, where it looks like just like what I said. Something happened in the middle there. A whole spray of particles comes out, but there's clearly something missing. Everything is moving this way. Something has got to balance the momentum that way. And in the underlying supersymmetric theory, the thing that's balancing it are the photinos that take off in the opposite direction. Okay. So that's one thing that we're looking for. In this first phase of operations, the LHCs looked for these superpartners. None of them have been seen yet. It's putting stronger limits on what the masses of these particles can be. But it's very, very early days in the exploration of this physics, and so we're all eagerly awaiting the updates as things move along. But the real thing that must be seen at the LHC, and what a lot of us it's really the first item on the agenda, is this Higgs particle. And one of the more interesting ways that it could be produced at the LHC is actually if you take a gluon out of the proton, another gluon out of the protons, these guys can pop out of the vacuum pairs of top quarks and anti-top quarks, and these top quarks have the strongest interaction of all with the Higgs. So they can actually produce the Higgs through being virtually created. They can also produce an excitation of this condensate that we see as the Higgs particle. And then this thing comes out, and again, it decays very, very rapidly. Just to give you an idea of the sort of the kind of difficult analysis that's got to be done, it turns out for a natural range of for masses of the Higgs, what it would want to do, and what it does the vast majority of time, is to decay to particles called the bottom quark. So bottom quark and an anti-bottom quark. That's what it does all the time. But that turns out to be very, very hard to see, because much more boring processes do that much, much more frequently. So in order to see that you've made a Higgs, you actually have to wait and have it roughly 1 every 1,000 times. It decays in this more exciting way into a pair of photons. This is much harder to fake, and that's what you actually have to look for. So the process of digging these signals out of more mundane backgrounds that are happening all the time is a very difficult, a very intricate, and a very interesting one. And this is just one example of the sort of thing you have to do. Often you've got to look for you're already making something that's very, very rare, but you have to pay a penalty to see its manifestation in an even rarer way, just in order to be able to see it over this roiling sea of complicated processes that are taking place underneath it. Okay, so you don't need to pay any attention to the details of this plot other than to look at this little box here. So really the big news of this year has been that we're in the end game of looking for the Higgs. Where it could be has been narrowed to a pretty small window. It could have masses anywhere, so this is these units are So with the 200 GeV means a mass of 200 times the mass of the proton, 300 times the mass of the proton. There was a sort of wide theoretical range that it could have been. There was a limit already from older experiments at around 115 times the mass of the proton. It could have gone up, let's say, to about 1,000 times the mass of the proton. And it's been excluded essentially over the entire range already, just from the data collected through to the end of this last summer. And we're now in this last window between around 140 times the mass of the proton to 115 times the mass of the proton. Now, that might make you pessimistic. They said, oh, it's basically gone. I mean, you're hanging on for dear life to a very, very small sliver of a parameter space, but it's actually not like that. For around at least 15 to 20 years, we've had a good theoretical expectation for where to expect the Higgs from indirect arguments. And those indirect arguments told us to expect it somewhere between 100 and 200. So this remaining, the part that's been excluded is the part that we sort of thought wasn't going to be there anyway. And that's what's so exciting about this particular few months that we're in now. A few months now to the end of the year, maybe through to the spring and to early summer if we're sort of unlucky, and it's in the hardest part of this window, is that we will find the Higgs if it's there and it has the expected properties. Okay? It's there somewhere. And it's where we sort of hoped it would be. And as I said, this is the really big story of 2011, that we're really in the end game of the search for the Higgs. And a final comment, I've said this already, but just to give you an idea of how difficult the actual analysis is, and any experimental colleagues in the audience will kill me for oversimplifying the story so much with a picture like this, but just to give you a rough idea, what we're looking for, the kind of rates of interactions at the LHC are something like this. There's around 1 billion collisions that take place every second. Okay? There are roughly 10 top quarks that are produced every second or so. Okay? Not quite that many now, but it'll get up there. It'll get up there pretty soon. Just to calibrate that, in 1995, the biggest experimental discovery in our field, which was done at Fermilab outside Chicago, was the discovery of the top quark. And after 7 years of running, they had produced 14 top quarks. They were very happy to have produced 14 top quarks, and then later they produced more, and of course, by now, they ended up producing a lot more. But it just gives you an idea of one of the maxims in this subject, which is that yesterday's discovery is today's background and is tomorrow's calibration. Okay? And so now this thing is so routine. It takes place 10 times a second. It's nothing. Now, what about things like supersymmetry? Well, if the superpartners are sort of roughly where we expect, then we're making them roughly once a minute. That's a kind of a picture of a rate. That's why the machine was designed in this way. So these things would happen at a nice human time scale, not once every century. It's like one a minute. That's a pretty decent clip. However, in order to be able to see them, you have to beat down these billion collisions that take place every second, these 10 top quarks a second. It's truly looking for a needle in the haystack. Okay? The only reason there's any hope at all is very roughly that the rate for producing more ordinary physics falls as you go to higher and higher energies. Whereas to the extent that if these particles are coming in with some characteristic mass, we'd expect that the events that are associated with them to be piled up at the energy scale associated with their mass. So there is a hope that we can, by understanding very, very well the rates for known ordinary physical processes, we can subtract them well enough to be able to dig these things out and find the needle in the haystack. Okay? The thing that I won't have time to talk about, but I'll be happy to address in questions, but which is quite remarkable, is that this part of the problem, the part of actually calculating and understanding these backgrounds, you would think that this is a sort of grungy part of the problem. You've got to do some sort of hard calculations and figure out exactly what the rates for all these processes is. And you have to do that to subtract it to see this exciting stuff. Well, it turns out that the 20 years that theoretical physicists, 20, 30 years, that have been spending trying to learn how to do these calculations, using the rules that were handed down to us by Richard Feynman, started realizing that around 20 years ago, people started realizing that these rules were terrible. They were completely ineffective. They weren't useful for the problems at hand. So that was a little startling, that the textbook rules just were not effective for the problem that they were needed for. And people started needing to develop new rules and new methods for doing these calculations. And those methods have led to a real flowering in our understanding of the basic rules that go into putting quantum mechanics and relativity together. And amongst other things, they're starting to give us what some of us think is a new picture for space-time and quantum mechanical processes that's not exactly the same as the picture that was handed us in the 20th century, and may well have something to do with this question of how space-time emerges from more primitive building blocks. So that brings us full circle back to the first question of space-time is doomed and what replaces it. And the amazing thing is that question seems to be connected with, certainly seems to have some deep connection with this grungy part of calculating known physics processes to compute these backgrounds and extract these little signals. So no good idea in physics is wasted. No good deed goes unrewarded. And I haven't had time to explain it in real detail, but there's a remarkable unity between all the different aspects of this subject. All right, so let me end. So we've gone through a long journey on what we learned about fundamental physics through putting together space-time and quantum mechanics, the general structure of quantum field theory, the essential difficulty or the essential feature that there are fluctuations of the vacuum, the incredible successes associated with those fluctuations of those vacuums encoded in the standard model of particle physics, which this is a wonderful accomplishment. But at the same time, we see that these pillars of 20th century physics also lead to these severe, severe paradoxes about the existence of the fundamental nature of space-time on the one hand, and on the other hand, how a macroscopic universe can possibly exist in a world dominated by short-distance quantum fluctuations. And we've seen that at least one of those questions, certainly the question of why there is a macroscopic universe, why gravity is weak, the question that has to do with what controls the big fluctuations in this Higgs condensate and prevents the electron from banging into it every 10 to the minus 33 centimeters, allows it to bang into it every 10 to the minus 17 centimeters or so. If we expect there to be some solution to that problem, it should show up at distances that are being probed by the LHC. Supersymmetry is perhaps the deepest idea we've had. It might not be correct, but I think it's theoretically the deepest idea we've had for what might solve that problem. And I've told you about what that might look like at the LHC. There are a number of other proposals as well, which I haven't had time to talk about. But just in a very big picture, what might we know in 20 years, in 10 years? So could it be that we see absolutely nothing at the LHC? Okay? But I mean nothing. No Higgs, no nothing. Okay? Well, sorry, nothing. Yes, nothing. Okay? And this is actually impossible. So let me quantify what I mean by impossible. I've made several bets with people of years of salary, by now 5-10 years of salary, that we will see the Higgs or something like it. And that something like it isn't a weaselly phrase. There's really something concrete associated with it, which is why there's so much confidence. And that is, if we just forget about the Higgs, forget about everything that I've told you. If we take the theory that we know and love, all the particles that we've seen so far, we can do thought experiments, and we can, using the theory that we have, without the Higgs or anything like that, we can calculate the rates for certain processes involving some of the particles that you won't care about. W particles of a certain helicity, longitudinal helicity W particles. You don't need to know what it means, but it's some process, a well-defined process that we can calculate. And if we just take the theory without a Higgs and anything else, we find that theory predicts its own demise. It just cannot be a correct theory down to very short distances. Amongst other things, the probability for something happening when these two slightly esoteric particles collide starts exceeding 1. Okay? You can't have probabilities exceeding 1. It violates very basic rules of what probability even means. And really more precisely, something new has got to happen or quantum mechanics is wrong. And there's no way quantum mechanics is wrong. I mean, quantum mechanics might eventually be wrong in some very, very subtle and strange way, but not yet. There's absolutely no reason for it to be breaking down here. So we need to see something. Absolutely rock bottom, must see something to solve this problem. Okay? So this is something that absolutely demands a solution. The theory that we have without the Higgs is manifestly incomplete, and so something must happen. Something new must happen. And that's something that so that's why it's impossible not to see anything. Does that mean that if we don't see the Higgs by the end of the year or by the spring or by the summer, everyone's going to give up and say there's no Higgs? No, absolutely not. It could mean that the Higgs is behaving in a slightly different way than we expect in this minimal standard theory. That might even be possible if there are, and it's even plausible in some of these extensions that modify physics, for example, in supersymmetry or other related extensions. So the properties that it could have could be subtly different, and the way you look for it would have to be subtly different. But I will guarantee you that if by August next year there's no hint for Higgs, or this window is closed completely, everyone isn't going to chuck it under a bus and abandon this idea entirely. Okay, it plays too important a role in ensuring something fundamental about quantum mechanics for something like it not to be there. Of course, it's entirely possible that we'll see something with exactly the sort of expected minimal properties as well, but that's what's exciting about these times. That question is going to have an answer on the timescale of months now. Okay, so now, what about these other things? So you see, the Higgs is something we must see. The Higgs or something like it is something we must see because our theory predicts its own demise, right around the corner. These other questions about the fine adjustments of the parameters is something where it doesn't necessarily demand a solution. After all, it could be that the parameters are very finely adjusted. Or it could be that we live in this gigantic multiverse, and the same kind of explanation that makes the value of the vacuum energy small will allow us to understand why gravity is so weak compared to the other forces. After all, if gravity was quite a bit stronger than it is now, those regions of this multiverse would also be lethal. So this is again, an anathema explanation for many, many physicists, but it's a logical possibility, and it's associated with the fact that this problem, these fine-tuning problems, are of a different character. They're not something where the equations break down. They're something where the parameters have some very, very strange-seeming values that seem to call out for a deeper explanation. But we're not absolutely guaranteed that they're going to have a solution. Nonetheless, I think it's entirely plausible that we'll see something like supersymmetry, and if we see it, to me, it would be not only euphoria for physics in general, but I think it would be euphoria for the community of theoretical physicists in particular, because this is an idea that has been discovered and run into so many different times by theoretical physicists in the last 30 years. It seems like such a deep and important idea that to see something that plays a role in the abstract world of ideas concretely realized in the world of the laboratory would just be extremely exciting and tell us that we're on the right track generally. Amongst other things, if this is discovered, it would be the first extension of our notion of space-time since Einstein. And it would explain that there's no fine-tuning for the question of why is gravity weak, although it would still leave us in the dark about the question of why the universe is so big, why this cosmological constant, this vacuum energy is so small. What if we see only the Higgs and nothing else? That's also a logical possibility. So we just complete the standard model and we don't see anything else. And that's the situation by 2020. I think that would be very, very confusing. But one thing it would be immediate evidence for is that there is some fine-tuning in the parameters that goes into describing our world. It's really a good thing that intelligent designers don't care about physics. Okay? They care that we're not monkeys. They really hate evolution because they don't want us to be monkeys. They don't care so much about physics. But if they did, they would have a much, much better argument. Okay? Because these are really situations where we do not, at the moment, have a particularly compelling explanation. Okay? We have so far, in the standard picture, do involve some fine-tuning. We hope that we'll see something like supersymmetry would give a beautiful solution for fine-tuning. I should stress again that this kind of fine-tuning argument has come up before in physics, and the strategy to look for a solution has worked multiple times. This is not the first time it's happened, and it's worked multiple times in the past. It could work in roughly the same way again. Okay? But if we don't see something like that, I think it'll be a first in the history of physics. We'll have some direct evidence sitting really in front of our face that there was some significant degree of tuning in the basic parameters that describe nature. And at that point, we'll have a real discussion. There's a real discussion to be had. I mean, at that point, I might start believing more gradually believing more in some sort of picture of a multiverse, because it would start unifying the explanations for the smallness of the vacuum energy and this problem as well. But on the other hand, just as a bald fact, we would see there is just fine-tuning in the parameters, and that would just be life. So that's something else which is possible. So these things are all on the table, and that's why it's such an exciting time. I just want to stress this. We're at a real bifurcatory moment in the history of our subject. And depending on what the LHC sees, I think we'll be thrown in one broad direction or another. The broad directions being that of order and chaos. Okay? If we discover these extensions of the Standard Model that solve these problems, find these extended symmetries of space-time, associated with these new pictures of unification and so on, this is the way physics has worked for the last 400 years, and it will continue working in that way, and it'll be a big boost to our ambitions along these lines. But if we don't see something like that, I think it's much, much more circumstantial, but it would begin to force people to take this modification of our picture of space-time at enormous distances much more seriously. But this is really, it's this bifurcation between order and chaos which is on the table for 2020. So it's been a long talk, but part of the reason it's been a long talk is that we don't know the answers yet. Once we actually know what's going on, it's a lot easier to not talk about all the different speculative things that could be happening, but talk about what is actually happening and what we've actually known and seen to be true. I think that's maybe the most exciting thing about the era that we're in now, is the sort of talk I've given today. This is like one of the few last times that this kind of talk will ever be given. No, I'm very serious. I'm very serious. We've been giving talks like this for 10 or 15 or 20 years, but the talks of the future, and I hope in future Brookhaven forums, will hopefully be about all the things that we're actually directly learning experimentally about physics at this length scale. What I hope I've convinced you of in this talk is that this physics is important. It's really important. It's associated with very basic questions that go to the heart of the revolutions of the 20th century in our pictures of space-time and quantum mechanics, and what we well propel us into the new revolutions of the 21st century. Thanks for your patience. Thank you.